with the review today. So we do have our Unit 1, Quiz 3. So this will be Unit 1, Quiz 3, Review. All right, Corey. Okay, so really what I'm going to do here, as I just mentioned, the mass and change notes, class data, your notes, the other stuff, and then we also have measurement notes. And so what I want to do for this review is I'm going to start off by, and these are the things that you want to take a look at and study. I want to go over your last quiz. Okay, sorry about that little delay, but I'm going to go over the quiz. I'm also going to go over the Unit 1 Worksheet 1. I think it was Worksheet 1. Yeah, Unit 1 Worksheet 1, which you guys just got back yesterday. Some of you just got it back now. And I'm going to talk about the measurement worksheet. So these are three things that we want to look at, and look at our notes as well, so that we're ready for the quiz tomorrow. So I told you guys that your first two quizzes, I basically, if you did better on the second quiz, it made up for both grades. So like if you did not so great on the first quiz, the second quiz grade could replace that. This third quiz is a separate quiz. So what's going to be on it? First of all, if I look back at your last quiz, which I should have up here somewhere. Right here. Okay, first of all, the pod C thing. Oh, I can't. Not going to do that this time. So no pod C. Okay, but there is going to be questions about variables. We do need to know our variables. And we need to be able to graph those variables. All right, so on the last quiz, the variable that changes because of the variable being tested. So we should know that the variable being tested, that's what we change on purpose. That's the one that is the manipulated variable. We are manipulating it. So if you look at number 4 here, the variable that an experimenter changes on purpose in order to test it is called the manipulated variable. So that's the thing that we're changing on purpose. So 4 was B. The thing that changes because of that is the dependent variable. All right? So I told you when you got these back yesterday, hopefully you have this stuff, or tonight when you're studying, you have these worksheets out and you can go over them with this video. That would be awesome. All right. We also have number 3, the part of a controlled experiment that does not change from trial to trial. These are the things that we want to keep constant. Okay. So 2, 3, and 4 went A, C, and B on your last quiz. Got that? You do still have to know manipulated variable, dependent variable for this quiz, and constants. All right, just going over the graphing stuff, you are going to have to graph again, of course. All right. So in this experiment, clams were placed into various temperatures of water. Use the information in the data table below in order to create a proper scientific graph and to answer the corresponding questions. So we have our different water temperatures. So this is what we're changing on purpose, which means this would be what we are manipulating. All right, so that is the manipulated variable, and hopefully you remembered from dry mix, a couple things you could remember, that the manipulated variable is also the independent variable. I felt a little kind of bad about that I didn't tell you or remind you, But so the independent variable in this experiment would be water temperature. But you should know that the dependent variable is the number of clams. Okay? The number of clams. It's changing because you changed the different temperatures. So you manipulated the temperature, and when you did that, it changed the number of clams that developed. All right? What is the optimum? Optimum means best temperature for clam development. So if I look at these numbers here, 140 is the highest. So that answer would be 30, and the units are degrees Celsius. Number 4, I told you to skip because we didn't talk about the mean. No, because you were wrong anyway. I'm just kidding. I probably didn't even look at it. Number 5, approximately how many clams would be developing in 10 degrees Celsius water? You guys did a nice job with this for the most part. So you were able to look at, well, here's 15. It was 72. 10 would be 5 less than that. If we went up by 5, it changed by 20. So a lot of people actually put 52. Okay? And it was just a rough like estimate, not an exact answer, but I was looking for something around 50. So that's pretty good. I was pretty proud of you for that. Identifying trends is what that's called. All right. Oh, and then we had to do all the graphing. So, of course, remember that we put the manipulated variable, which in this case would be water temp, should go down here. We did have some people that put the wrong variables on the wrong axes. So again, dry, mix. Remember that the manipulated or independent variable goes on the x-axis, and include your units. All right, which means number of clams goes on this one. And we don't really need to put units for that because it's self-explanatory. It says number of clams. I mean, that's what it is. We should also have a title of some sort, maybe clams, number of clams in different temperatures of water, something like that. And then we got to figure out the appropriate scale so that we use the majority of the x-axis, and the appropriate scale to use the majority of the y-axis. And then the graph should have looked something like this. Okay. How do we find the slope of that line? We don't. Okay. We need a straight line. Straight line, we could find the slope. Okay. But you're not going to have to know slope for tomorrow. Slope will be on the next quiz. All right. But you should know your variables and your graphing. All right. So then make a model explaining particle arrangement in a glass that is half full of water. So on this, I mean, I was looking for a title. Glass half full of water. Maybe you did some little kind of line across here, and then show me particles. The other thing I might have liked to see is a label. So we label the big things. We don't need to label the particles. We'll use a key for those. All right, what are the black dots? So we need a key. Black dot, water, particles. All right. Not a whole lot to explain because it's not a process. This is one of the rare occasions where I'm just asking you to show me a snapshot in time. Usually we don't do that with modeling. We show a process or explain a process. All right, so now the other thing is, I didn't grade people down, but really if we're talking about the particles in this glass, are the water particles the only particles in this glass? They are not. And some people did like oxygen and stuff in the water. I noticed that in this year's group, a lot of people are really concerned about the oxygen in the water. Don't be. Just think of it as water. What's in water? Water. All right. But above the water, in the glass still, there could be air or oxygen, whatever you want to say. I would just say air particles to keep it simple because realistically it's not just oxygen above it. It's mostly nitrogen actually. Okay, so that should do everything for that, for modeling. Okay, get through this. All right, that's that. So the next thing that we did was the Unit 1 Worksheet 1, which is this one. So you should have gotten this back. And pay close attention to this because I did notice some issues here. Okay, so if you have this worksheet, I highly recommend that you look over this worksheet with the correct answers on it and study it. A lot of you got a lot of points wrong on this. I was grading this for quite a while, writing in corrections. So um, the first part, number one, when you pulled the steel wool apart, you found that the mass did not change. Okay, so that's what was supposed to happen. The mass didn't change. We know from actually doing it that some of the steel wool stuck to our fingers or whatever, so we might have saw a loss in mass. But if it's just pulling something apart, the mass shouldn't change. Whatever particles we have at the beginning should still be there at the end. However, when you heated the steel wool, you found that the mass changed, right? Yeah? You guys staying with me? So if I do steel wool pulled apart, all I'm going to do is in this box, maybe I just kind of draw a picture. Now, the steel wool wasn't a square, but just for the concept. Maybe I make 3 particles on each side. Thank you, Kayla. And then over here, I'm going to draw the same thing, but the square kind of ripped apart. And maybe I put 3 dots in each thing. Now, the main idea with all of this mass and change lab, the main idea for this, don't forget, was the law of conservation of matter. This is the big idea, okay? You guys have to understand that that is the big idea. Does everybody see that? Everybody looking at that? Okay, so what this means, guys, main idea, pay close attention. For all of your models in mass and change, all of your models, your before and your after, because of this law of conservation of matter, always have equal number of particles. Always. Now, when I say that, it might just mean in the box. Okay? Okay, so in the second one, how did the mass change for steel wool? According to what I told you, how was it supposed to change? When we burned it, it's supposed to gain. Do you remember why? Oxygen in the air is involved with this change, okay? So what that means is if I've got my steel wool beforehand, like this, and maybe I draw 4 particles, okay, and then here at the end, I want to show that it gained. I still have to have those 4 particles, but if we're going to say that oxygen joined in this change, okay, so this right now does not show conservation of matter. I started with 4 particles, and now I have 8. Okay, so the difference is, and I would have a key here that says red is steel wool, Black is oxygen. So that means I just need to, over here, make sure that I put those 4 dots up above. So now we show law of conservation of matter. You should always have the same number of particles of the same type in each picture. It should never change. Maybe particles got released in the change. That's cool. You can still draw them in the box somewhere up in the air. All right. Maybe the mass stayed the same. Okay, so whatever particles you started with, you have at the end. Maybe they were added. So I had some particles that are up in the air in the before, and then the after they're in the substance. Okay, does that make sense? All right, when ice melts, the volume of water is smaller than that of ice. How does the mass of the water compare to the mass of the ice? That should have stayed the same. Okay, should still be the same number of particles in there. Shouldn't change. Use small circles to represent the particles of water or dots. Draw diagrams, ice and water. So ice, did this a bunch of times. It should be in your notes too. So ice, here's a couple cubes. Put a couple dots in each. And then we have the water. And I would still be sure to make 4 dots, okay? Still got to have those same 4 dots. So there's a total of 4 dots in the before, total of 4 water particles in the after, law of conservation of matter. All right, a lot of people either skipped number 3 because they didn't realize it was a question or got it wrong. But what happened with the Alka-Seltzer? How did the mass of the system change? So we took some Alka-Seltzer and we dropped it in water. It bubbled up. That was station 7. Jerry? Okay, some of the particles left. All right. So here's another thing. If we have more than one thing that we're combining at the beginning, you have to show that. So on this one, I would have a beaker that had water particles. Okay, maybe I show just a few of them. Remember, we don't need to make a ton of them. And then we also had a container. Oh, no, we didn't have a container, but we had Alka-Seltzer. All right, make it a square. I'll make the Alka-Seltzer green. Okay, now was this a chemical or a physical change? It was chemical. We know because we saw the bubbles coming off. So we're making something new, which means we're probably just combining these particles. So in the after, what I would do is in the after, I still have to show that I have 3 blue dots and 3 green dots, 3 water particles and 3 Alka-Seltzers. But when they stick together and form different compounds, they can change properties like having lower density and floating into the air. All right, so what I might do for this is put a green dot attached to a blue dot here, okay? And then up above, escaped into the air, I might do a couple greens attached to a couple blues, something like that, okay? So if you look at it in each picture, there's still the same number of dots, but now in terms of what we're actually finding the mass of, it's only 2 particles there, so it would be a loss in mass, okay? Oops, that was the Alka-Seltzer one. Sugar and water, again, you have to show you have 2 containers now. Here's water, and then sugar. So water, I'll make maybe 2 particles, and sugar, I'll make that black. I'll make like 3 particles. And so if I put the sugar in with the water in one container, it's just going to look like this. Still 2 blue dots, and still 3 black dots. Okay? So we have a total of 5 particles in the beginning, and we have a total of 5 particles at the end. That means the mass should not change. Law of conservation of matter in your own words. Well, in my words, matter cannot be created nor destroyed. That's the main idea. So that in each of these pictures, if I'm doing a model, whatever number of particles I have in one picture, of each type has to be the same as in the after. If I want to be more specific there, I have 2 blue before, and I have 3 black. I better have that same number of each at the end. Make sense? All right, almost done. All right, so the last thing is you got to be able to do measurements, volume measurements tomorrow. And they got to be not only accurate, but they got to be the right level of precision. You guys are pretty good at looking at the accuracy. You're actually pretty good at the precision now, too. So lowest point here, here's 20, here's 30. I got to understand what each mark means. So on this particular graduated cylinder, each mark is worth 2. So that's at 24. This one here, each mark is at 1, so that's about 9. This one is about 40. So that's accuracy. That's easy enough to do. All right, but what we talked about was the correct level of precision. So the correct level of precision depends on the instrument you're using to make measurements. Okay? The way we do that is look for the lowest mark on the measuring instrument and estimate 1 spot further. So your last digit of any estimate is always an estimate. So if I look at this, and this is kind of the tip I gave to do this, I said make like 4 dashes with a decimal point in the middle. All right, and ask yourself a question. So this is the tens place here. Can you see all the tens? I can see 10, 20, 30, 40, 50. They're marked on that graduated cylinder, so yes, I can. Can I see all the ones? Well, when I look at the ones, I can see 22, I can see 24, I can see 26, I can see 28, I can see 30, I can see all the even numbers. But I cannot see all the ones, so I will not put a check mark there. All right? So that means my lowest value that I can actually see on the graduated cylinder is a tens place. So I'm going to estimate 1 spot further than that, which means I would estimate the ones place, which means that's where I'll stop my measurement. So that first measurement should have been 24 milliliters. Now on this one, if I do the same thing I just did over there, so 1 dash, 2 dash, 3, 4, can I see the tens? Yep, I see 10, I see 20. Can I see the individual ones this time? Yes, I can. I can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so on this one, if I can see the ones place, I can't see anything lower than that. I can't see the tens place here. So I'm going to estimate that tens place. So I can tell for sure, you know, it's between 8 and 9 or right at 9, whatever you think. If you think it's right at 9, you would put 9.0. But you've got to have that 1 decimal point until in order to have your credit on this quiz. Okay? If you put just 9, you get it wrong. You got to put 9.0. If you put just 8, it's wrong. You put 8.9, it's right. You put 8.8, it's right. You put 9.1, you're right. You put 9.10, you're wrong. Does that make sense? You have to go to the correct values. So here I can see the ones are marked on this one, so I would go to the tenths place, so that would have 1 decimal place. This, all the ones are marked, so I would go to the tenths on here as well. Here it's back to marking every 2, so I would go ones place would be my last digit, would be the estimated digit. All right, so after that we did something easier. So like I said, all those are in milliliters because it's a graduated cylinder. But on the back side, oh, displacement. Okay, so displacement. We start with a certain amount. We add an object. How much did the volume change? What's the difference between those two? That is the volume of the object. Okay, so if it started at 17 and went up to 22, that has a volume of 5 milliliters. That's by displacement. Okay, and then if we do a regular solid, a rectangular prism, like we did with the plastic cube in the lab, you're just going to take 3 sides and multiply them together. So here, these measurements are in centimeters. 4 centimeters times 6 centimeters times 2 centimeters 4 times 6 is 24, times 2, that would be 48 centimeters. And since it was centimeters times centimeters times centimeters, 48 centimeters cubed. So you just multiply the 3 different sides. Okay? So, graphing, variables, mass and change lab, you should know what happened at the different stations, and you should be able to model what should have happened, paying attention to the law of conservation of matter, and then the measuring that we have right here.